Good afternoon, ladies and gentlemen, and thank you for joining us today on this webinar, Photonic modules for Lidar and sensing applications. So I'm Adrian Chance, Head of Marcom for the G&H Group, and joining me today for the session today is Toby Reed, Product Director for our Fibre Optics section, Dr. Peter Keane, R&D Director, Fibre Optic Systems, and Sam Sell, Fibre Optic Applications Engineer. Before we move on, I'd like to just perhaps ask you if you would like to participate in a brief poll. So it's two questions. Do you manufacture LiDAR or sensing systems? Is the first question. And there you are. So let's select one of those questions. And this is simply really to ascertain, really, I mean, perhaps your interest and you know, you might be here for educational purposes, or you might actually work for a manufacturer of such systems. And then the next question is detection sensibility. Is detection sensibility? Sorry, when the poll comes up, is detection sensitivity a critical performance factor in your systems? So that means really in the systems you provide, are they perhaps more commoditized systems, or is it are you trying to seek competitive advantage through increased detection sensitivity, perhaps in challenging environments, or perhaps where sensitivity is a key issue for other reasons? So perhaps if you can just indicate that. Thank you very much, ladies and gentlemen. That's very interesting. Was very interesting results there. We can see that from that not everybody is involved in manufacturing such systems, but for those that are, that sensitivity really is. So thank you very much. That's helpful to us, and certainly something we touched upon during the course of today's webinar. I'd like to hand over now, please, to my colleague. Toby Reed, Product Director, who will take us through the opening part of this of today's webinar.
Thank you very much, Adrian, and hello everyone. I'm going to talk a little bit about the applications for LiDAR sensing systems that are relevant to our webinar today. So the applications fall into two main categories: distributed fiber sensing and atmospheric sensing. Firstly, distributed fiber sensing started with optical time domain reflectometry, or OTDR, which was primarily used for detecting fiber faults and fiber breaks in telecommunication systems. But since that time, the number of applications and the complexity of the systems has increased greatly. As the name suggests, in these systems, fiber sensing systems, the optical fiber is the sensing medium. So the optical fiber forms a long and continuous sensing medium. When light is traveling in optical fiber, should there be a disturbance to the optical fiber, then some of the light is back reflected towards the source. These disturbances might include local changes in temperature, local changes in pressure, or vibrations. The Lidar technique, the time of flight technique, allows the position of these disturbances to be located. So this technique, with a long and continuous sensing medium, lends itself to the monitoring and protection of very long pieces of infrastructure, often called linear assets. So, for instance, a border or a fence or a wall might be monitored and protected with a distributed fiber sensing system. A fiber buried alongside, under the ground alongside the wall, if someone should go near that wall or border, then the fiber sensing system would detect that event, and the LiDAR method will locate the position of that intrusion, for instance. The same technique can be also used to protect other long pieces of infrastructure. Unfortunately, nowadays, when infrastructure is built, long pieces of infrastructure is built, fibers are often laid aside alongside that infrastructure. So, for instance, the traffic on roads can be monitored here. Disturbances to railway lines as they travel through long, remote locations without people can be monitored. Long pipelines carrying oil and gas can be protected and monitored, and power lines and other utilities can be monitored. Fibres can even be deployed down the drill hole of oil rigs, allowing sort of changes in pressure in the drill hole to be measured and the system efficiency of the oil rig to be optimized. These systems typically have a range of 10 to a few tens of kilometers, maybe even 100 kilometers. But when many sensor heads are combined and concatenated, then they can be used to protect very long structures, even up to thousands of kilometers in length. For instance, oil and gas pipelines as they traverse continents. So that's distributed fiber sensing systems. The second category of applications relevant to our webinar today are atmospheric sensing systems or remote sensing systems. The principles of these systems are very similar to those of fiber sensing systems or distributed fiber sensing systems. But instead of the light being launched into an optical fiber, the sensing medium is the atmosphere or the sky, and objects within the atmosphere are detected using the Lidar technique. So for instance, this technique can be used for surveying. And this photograph here on the top right shows, it looks like a standard piece of surveying instrumentation, but in fact it's a Lidar head, and it's scanning a beam in 2 dimensions at the scene in front of it. And in that way, it can build up a 3D image of what's in front of it. The third dimension, or the depth dimension, comes from the Lidar technique. So here the range might be a few tens of meters for scanning building sites and archaeological sites, for instance. If the scanning head's mounted in an aircraft, the range can be greater. And the technique can be used for environmental applications, such as monitoring deforestation and looking at the topology of the ground. And now, even the surface of celestial objects, such as meteors and planets, can be mapped with this Lidar technique. When objects in the sky are moving, their position can be located with the Lidar technique. But also, moving objects create, when they back reflect, they create a frequency shift due to the Doppler effect. And this frequency shift can be used to determine the speed of the objects. So both position and speed of objects in the atmosphere can be monitored and detected. And this technique is very useful in applications such as wind power generation, where a Lidar sensing head might be mounted on a wind turbine that can make a 3D image of the wind in front of the wind turbine. And this information can be used to optimize the power generation from that wind turbine. Dust in the air scatters light, and the speed of that dust tells you about the speed of the wind. The same technique can also be used to monitor the wake of aircraft at airports. When aircraft take off, they create turbulence, and backscatter from the dust kicked up by the aircraft can be monitored. And this can be used to optimize the efficiency of the aircraft, decreasing the time between takeoffs and landing, so the knowledge of where the air becomes still again is very useful. So you can see there are a great many applications for Lidar sensing systems, both in fiber and in the atmosphere. Before we go on to talk in detail about the optical hardware needed to make a Lidar sensing system, I'll just show you a brief schematic of how that hardware might be arranged. More often than not in these systems, time of flight of an optical pulse is used to determine position. So the transmitter of such a system needs to create an optical pulse. And that can be done with a continuous wave source, an optical switch, and then an amplifier. And the amplifier is needed because very often in these systems, the amount of back reflected light is very small. Only a few photons might be backscattered by dust in the air, for instance, or from a small disturbance in fiber. So with a CW source, an optical switch, and an amplifier, we create a high power pulse, which we then launch into the sensing medium. If that sensing medium is optical fiber, then the launch is simply achieved with a pair of optical connectors. But should it be the atmosphere, then a beam of light is needed, and a beam of light can be created at the fiber end using a fiber optic collimator, which can accurately control the collimation, beam weights, beam diameter, etc. So now we're going to talk about some of these components in detail and how they're used in LiDAR sensing systems. And I'm going to hand over to my colleague, Dr. Peter Keane. Thank you very much. Peter, over to you.
Thanks, Toby. Hello, good morning, good afternoon, wherever you may be. Yeah, thanks, Toby, for the for that kind of introduction to the applications and the transmitter sort of subsystem of LiDAR systems. So what I'd like to do is just to kind of briefly go through some of the components and the key performance parameters of the components that are used within such a subsystem. And as we go along, please do feel free to type up and add any questions into the question box there, and we can try and address those at the end of the session. As Toby mentioned, this diagram shows the transmitter subsystem and also perhaps a small part of the receiver subsystem down here, just to kind of illustrate you know, how the signals are detected, if you like. And this particular detection system uses part of the source light with the receive light to form a coherent receiver, which I'll come back to in a little bit more detail shortly. So if I begin at the beginning, as it were, we're talking about the laser source. What are the important characteristics for a laser source? And we typically use, I mean, more or less any kind of laser can be used. And in fact, if you're not doing a coherent detection, then in fact you could use a solid state laser or a diode laser of any kind. And basically you would try to make that a pulsed source so that you could do ranging and through time of flight methods. Typically nowadays, to improve both sensitivity and the parameters of the medium that we're able to sense, systems operators are using coherent detection, and for that you need a narrow line width source. So one such source is a DFB laser, or distributed feedback laser, and that's a semiconductor diode laser with a periodic grating on the surface of the chip, and that helps to produce a very narrow line width. And I show in one of the figures here, this first figure, show a measurement of the line width, and this is measured using the delayed self-heterodyne technique, and we can typically get line widths of around about 200 to 300 kilohertz from the laser source, with being a DFB. Now that does rely on having a low noise current source to the laser. One thing you find is that if the current, the drive current to power the laser has any appreciable noise on it, that can certainly broaden the line width that can be achieved. And that's really because the laser wavelength actually changes slightly with current. So if there is any ripple or noise on the current, then that translates directly into a broadening of the line width, which is not always desirable, particularly for coherent systems. The other thing about DFB lasers is that they are tunable over a limited range. Obviously, they are designed to be a fixed wavelength and stable, which kind of goes against the sort of the mantra of tunability. However, they can be tuned in wavelength, because actually as you alter the temperature of the device, and typically these lasers have a temperature controller called a Peltier device inside them to control the temperature. That not only helps to keep the wavelength bang on where you want it, but also as you tune the temperature, you can actually adjust the wavelength of the device slightly, which is useful if you've got other wavelength selecting components within the optical chain down the line. And so obviously, because it is a narrow line width device, we can have quite narrow channel spacing. So we could multiplex these systems and actually have several beams coming out into the sensing medium at the same time, for instance, if that was a particular system design parameter. The DFB lasers today are available at pretty high power levels, and by high power level, we're talking about sort of 80, 100 milliwatts, something like that. So that's plenty of power to overcome any system losses down the chain before we actually get to the optical amplifier, which will obviously boost the power further. And then we also certainly kind of within our company G&H, we're always looking at real world applications here for these devices. So we would produce packages that are hermetically sealed, so they're resistant to environmental effects such as humidity and so on, so that as a system builder, you know that these components can be used outside in the real world, wherever it may be that in the heat of the Sahara Desert or the freezing cold of the Arctic kind of thing. The final bit, which I haven't mentioned yet, is perhaps the noise level. This is a typical plot of the DFB laser relative intensity noise, or RIN level. And again, that's an important parameter to keep the noise level low, so that we can achieve, or you can achieve much better sensitivities in return signal detection. And again, this is really quite a function of the drive current that is applied. So good electronics design to be able to drive the laser is important there. So that's the laser source. Pretty much a commodity component these days. A fused fiber optic coupler is absolutely ubiquitous in fiber optic networks and any kind of fiber optic system. And I really mention it just because of it's such a useful and basic component these days. In any of these systems, we need to split the light, maybe multiplex light, combine power and wavelengths. And it has become a real key component in telecoms and indeed Lidar systems as well. And some of these, the graphs here, I'm just showing various parameters, wavelength dependence. We can achieve quite a broad band coupling ratio over a broad band of wavelengths if that was required. And then also basically the product control and quality control that we tend to have for fused fiber optic couplers. So if you're specifying a particular, say, an 80-20 split coupler, we can manufacture that to within plus or minus 1.5% tolerance, and that's sort of data taken over more than 1,000 units. And similarly, excess loss. We obviously want to know that any components that are added are really not taking away any photons that they don't need to, and so you really want as low loss components as possible. And again, that's kind of some manufacturing data actually that shows that we feel we've got very good control over the manufacturability of those components. And they can be obtained in PM and SM and indeed even multi-mode fibers. And again, they're kind of sealed and very well qualified for environmental performance. So the next component actually is associated with fiber optic amplifiers, and the way that those are operated, essentially you need actually a semiconductor diode pump laser to activate and pump the erbium fiber that's in the amplifier. And some of the some of the key parameters here. We have either single mode pumps or multi-mode pumps can be obtained to pump. Single mode pumps are generally available up to 700, 800 milliwatts or so with a very narrow line width, and they tend to be Bragg grating stabilized so that you can pump accurately onto the absorption line of the erbium. Multi-mode pumps are generally a little bit broader in wavelength, but you can achieve much higher output power, so up to 9-10 watts or so. And they're really designed for double clad fiber pumping of erbium amplifiers, and really that's to help obviously get much higher power levels out of the amplifier and get higher peak powers, which can be launched into the atmosphere or the fiber to aid detection sensitivity and the ultimate detection of very low light signals. So that's just something briefly about the fiber pump lasers. Another kind of fused component that we've worked on actually is called a tapered fiber bundle, which is slightly different to a classical fused fiber system in that, and it's constructed as this picture shows very nicely actually, of a single fiber in the center surrounded by the multi-mode pump fibers, and those are bonded and fused to the center fiber. And what we can do is launch, in this case, up to 6 pumps into this fiber or construction, a tapered fiber bundle, and then that can be spliced onto a double clad fiber and allow very high pump powers to be obtained. And that's used very successfully, not only in sort of Lidar amplifiers, but also in free space optical communications for inter-satellite links, for instance, where the distances involved are so great that you really need to get as high powers as possible on the data, on the optical data signal. Okay, so moving on. So one of the key features of a Lidar system is to be able to create an optical pulse. And one of the key ways that we do that is to use our acousto-optic modulator, which we call a Fibre device. And this is based on the interaction of light by ultrasound. And just to kind of briefly go over how that works, essentially you have an RF drive signal which might be producing a signal in the region of anywhere from 80 to 200 megahertz, something like that. It's applied to a little transducer which vibrates and produces an ultrasonic pressure wave, or acoustic wave if you like, inside the crystal or material. And those pressure waves essentially create regions of obviously of high pressure and low pressure within the medium, and therefore that causes a refractive index change in the medium, and this pressure wave then forms a refractive index diffraction grating effectively. And so by bringing in the input light, we can get diffraction into one or more diffracted orders. Now, as the light is in this arrangement here, we see that the light is, I've kind of indicated that it's largely diffracted into just the first order here, which is a very efficient method of operating these devices, and we can get well over 80%, nearly 90% diffraction efficiency into that first order. So by having a launch collimator here from the fiber optic source going through the Bragg, the acoustic diffraction cell here, having a collection collimator aligned up with the first order diffraction, we can obviously produce a modulation simply in the light simply by turning on and off the RF drive signal. And we can do that pretty rapidly to create pulses of just a few tens of nanoseconds or longer. And depending on the particular diffraction medium that we use, we can vary the rise and fall time of the pulse shape. And so by modulating the RF drive signal, we can produce actually not only just simple Gaussian type or rectangular type pulses, but you can indeed even modulate the RF drive and produce more complex pulse shapes. And that's actually quite useful sometimes when the pulse has to go through a bit of some amplification and fiber transmission later on, because it can see changes due to the amplification, and we can actually pre-shape the pulse so that we get, in the end, we're actually launching a nice clean Gaussian shape into the sensing medium. And the other effect of these acoustic optic modulators is that not only is the light diffracted by and modulated by the sound wave, but also the light actually produces a frequency shift on the light. And that frequency shift is simply equal to the RF drive frequency that's used. And you can consider that as because of the Doppler effect of the sound wave moving across the beam and therefore imparting a Doppler shift onto the light. And that becomes very useful again in coherent detection schemes, where, as I show in this little copy of the little schematic here, we actually pull a section of the source laser before the modulator and before the frequency shift, and that is combined in the receiver with the sensing return signal, which of course will have the optical frequency shift on it. And then by doing a coherent detection there, we can actually pick out very sensitively pick out the optical return signal, because you know that you're looking for a particular frequency shift, and the beat signal is what you look for, and you can very narrowly selectively filter that out. So that's some basics on the fiber optic acoustic optic modulator. Some of the key parameters that you would look for in this kind of device is you would want a high extinction ratio. So we know that the system is really off when it's turned off. Typically we're getting 40 to 50 dBs of extinction ratio in these devices. They're also broadband, so it can operate over a wide wavelength range, and it can provide a frequency shift, up or down frequency shift equal to the RF drive frequency as I've described, and again a key parameter here is that it allows you fine control of the pulse shape should you require that in the system. It's also high power capable. So here, I think I'll show that actually in the next slide, but the insertion loss of the FibreQ device can be gotten down to just over 1 dB, 1.5 to 2 dBs. So really quite a reasonably low loss optical switch here. And as well, the insertion loss does also, for a particular device, particular design of a device, the insertion loss does depend on the RF frequency, and that's fundamentally that's actually governed because the diffraction angle is dependent on the RF carrier frequency. So as the carrier frequency changes, the diffraction angle changes. Now, in some devices, that's actually very useful because you can use that as an acousto-optic tunable filter, or AOTF. And at Gooch and Housego, we're actually very proud to know that one of our devices is currently on Mars, within the NASA's Perseverance rover, and it's being used for spectroscopic analysis of the signals that their laser is picking up from the surface of Mars. So that was a very exciting project for us to be involved with. Okay, and Yeah, I mentioned the high power handling. So this is just a slide to show we've done some testing up to 7 watts here of power handling, and we can see that there was no real degradation in the system over a few hundred hours of operation. So we were probably launching about somewhere around 8 to 9 watts into there, and because the undiffracted beam, which is the section that is lost within the device unavoidably, is essentially dissipated into the metal wall of the housing, it is a device that can reliably handle very high powers as well, which can be very useful. Okay, so moving on to the receiver subsystem, I just want to talk about one particular aspect of the receiver subsystem, which is the coherent receiver, the optical receiver, and a development of that we've kind of worked on over the last couple of years or so. And just to introduce that, essentially the receiver or a coherent receiver is essentially formed of a 3 dB coupler, so a 50-50 coupler, with 2 of the outputs going on to a pair of photodiodes. And as the return sensing signal is combined in that coupler with the local oscillator signal from the source laser, essentially interference occurs in the coupler, and the balanced photodiodes here will only detect, in fact, that the signal is picked up from the midpoint of the 2 photodiodes here, and that will only detect the interference signal between the 2 inputs. Any common mode noise on the any noise on the local oscillator, for instance, is quite effectively filtered out by this scheme, because both photodiodes would be detecting the same noise signal, and therefore at the midpoint the signal is essentially 0. So it only detects the interference signal. Now we've taken that sort of basic principle and we've developed what we call the Optical Polarization Diverse Receiver, or PDR. And in that case, we've used this receiver system for a number of different applications, including Lidar, but also optical coherence tomography, or OCT. And essentially we bring the 2 signals into the 3 dB coupler again, but afterwards, following on from that, we actually split them again into with polarization beam splitters. So essentially here we can launch the local oscillator signal at an angle of essentially at sort of 45 degrees, if you like, into the polarizing beam splitter, so that equal amounts of the local oscillator signal is detected in both orthogonal polarization states. And what that means is that if you combine the signals correctly from the photodiodes, it means that you become much more immune to any polarization fading issues. Obviously, if the sensing signal happens to be comes in at the orthogonal polarization to the local oscillator, then you would tend to not get any interference, because interference only happens when the polarizations are aligned. So in this scheme, because we combine and polarization split, we're able to detect the interference signal no matter what the polarization is of the incoming sensing signal. And that's can be hopefully very useful for Lidar detection systems. So this is basically a little shot of the device and the schematic of the arrangement inside. So again, this is just basically the beam combiner and then some polarization splitters, and the package contains 4 photodiodes in this kind of package of about 42 by 30 millimeters. And we're quite excited by this new product. It's giving about 35 dBs of common mode rejection ratio, so we find that it's really effectively rejecting any common mode noise. And we've developed that so it can be operated at different wave bands. We have different variants for the different applications, really. And it has a high optical bandwidth in the region of, we use photodiodes that can give us just over a gigahertz of bandwidth there for detection. So that's, briefly, that's our polarization diverse receiver. The final thing that I was just going to talk about was the optical amplifiers and optical pulsed amplifiers in general. I've covered kind of most of the components, but we are involved as well in building up these amplifier systems. We've got very good capability in high power handling of both components and fibers to enable these systems to be put together as a combined unit. And we've been involved with EDFAs, erbium doped fiber amplifiers, and also erbium ytterbium fiber amplifiers, which, as I mentioned earlier, they tend to kind of produce even higher powers with some of those multi-mode pumps. With that, I think I'd like to hand over to my colleague Sam Sell, who can talk a little bit more about the kind of more about the systems aspects. Thanks very much indeed.
Thank you, Peter, and hello everybody. As Peter has been through all of the components now, as he said, I'd like to move on to the sort of the modules and subsystems. So if we go onto this initial slide here, you can see on the left-hand side of this diagram, that's you guys, the sensing OEMs. And you have an initial concept idea which you develop from your understanding of the markets that you're involved in before moving on to sort of a prototype system design. And then you'd iterate that through into a sort of a robust solution which you can then launch into those marketplaces. So over on the right hand side here we have us, Gooch & Housego, and what we would like to do is of course supply these components that you require into your system, but additionally to that, if we could manufacture some of these subsystems or modules for you, that would be really what we'd like to be involved in. So in this middle section here we can see there's also the idea of G&H sort of subsystem design. We could work with you sort of early on in your development, so we could feed back some ideas, particularly for our sort of volume manufacture, which is an area which we've been working in for many decades there. So the idea of streamlining the processes and some of the designs to make it more applicable to that side of the volume. And of course there may be some subsystems you want to manufacture separately. We could integrate those together. Whether that's into subsystems themselves or into an overall system that would be the solution for you. So if we move on to the next slide, I'd just like to talk a bit more about the sort of design capabilities that we have here in Gooch & Housego. So as I said, we'd love to be involved early on in your development, where we could give feedback. We have dedicated design engineering teams, and we continue to design internally with our components, where we're continually moving on and trying to increase the capabilities that we have there, but also with our subsystems as well and our modules. So we'd have, of course, electronics design capabilities for complex PCBs, and with components like our PDR. As we continue developing them, we're continuing that with a pallets detector board, so it would enable more simple integration into your systems as well there. So of course we'd have optical design engineers, mechanical engineers. You can see a couple of these images here for stress and strain modeling and some optical modeling, which again we perform across our range of components as well. So let's move on to the next slide. So you can see this gives a good visual indication of how we could start to involve our components into modules and subsystems. So there's a selection of components here which we could tailor to your requirements and your needs to make sure it's the exact fit for the system that you've designed. And then we could move those through into into modules or subsystems themselves. So we can see about this this receiver unit here, which would involve some couplers and PM splitters. So we could then split that into the PDR which we've developed, or maybe an entire receive system itself into a single module or subsystem. And we could do the same thing with the transmit unit, whether it was the source that could be manufactured separately before being integrated, but also other areas with such as the optical amplifier, or even splitting that system into more modulated idea, and then we could bring that all together for you as a robust solution there. So we talk a little bit about our manufacturing centers. So we have 2 fiber optics manufacturing facilities. We have one in the US in Boston. We also have one in the UK as well, down in the southwest of England. So these 2 sites, they share some amount of management through G&H, whether that's through operations and through engineering. So there's some potential of shared resources there and knowledge sharing. Very large sites, over 8,000 square meters production floor space. And we're always trying to extend our facilities and increase our capabilities, of course, our equipment and our operators and staff as well there. So we have certifications of ISO 9001, but also the AS9100 standard, which we've had in the UK for the last few years now, with our yearly audits, which we continue to excel through. As I said, through this development in our facilities, we're always increasing our capability. So through our clean room standards, so we're improving our clean rooms with segregated areas to higher specifications, more clean environments for particular markets. And that's something we continue to try and do all the time, and just keep our improving and refining what we do. And within these facilities, we have specified areas within them for fiber optic assemblies. They may be within their own cells with their own strictly trained operators for the processes for the manufacture of those modules. But they do also have a team around them. So they'd have team leaders, technicians, which will be intimately involved in all those processes for those particular builds, but also product engineers and manufacturing engineers, which are always looking to try and streamline and improve the processes we use to try and create as a robust solution as we possibly can on everything that we do. So if we move on, of course, there's different possibilities of what we could do for you. You may have a build-to-print solution which you need us to provide for you in larger volume. But equally, you may need some help with design for some different facets of the system that you're building, and we're more than happy to be involved in either of those possibilities. So with our dedicated design engineering team, we can feedback from our manufacturing engineers to help from a very early point make it as manufacturable as possible. Of course, there can be IP and security and controls. We're having a site in the US as well as a site in the UK. There may be some ITAR restrictions from the US, but also when working in markets, we're very used to working with competitors within those markets, and we've done that also for decades now in different markets. It's incredibly important to isolate the IP across those different customers, and it's something we have a great deal of experience in and continue to do so with our procedures on a day-to-day basis there. Another important aspect that we like to take hold of is the bill of materials. If we can control the supply chain, that helps in 2 ways. It helps us. We can control our materials onto site, making sure they're here at the right time for when they're needed, so we can achieve the lead times that we give and the shipping dates that you need. but also it's an activity that doesn't have to be performed by yourselves. So it can lighten the load for you somewhat there. And of course, we will look at the conformity of products to make sure they're fit for purpose into the products that we produce there. And we perform this, of course, on our own components that we manufacture, but we do this across our subsystems and module builds as well. We're just as happy to use our own components, which we design and manufacture internally, but also third-party components. If there's particular requirements that you have, we're happy to take those on and use the components from third parties and integrate them into the system. We continue to do that, and we've done that for a long time also. Within the operators training, we spend an awful lot of time with them early on to develop their fibre handling, their routing, their splicing capabilities through our extensive equipment we have of splicers on site, whether that's PM or SM or maybe multi-mode, or even a photonic crystal fibre, which we've used in the past. So you can see in some of these images here, there's some lovely fibre routing, and we make sure that this is repeated every time. We create very detailed instructions for build, and there's constant support from the engineering team, and an awful lot of knowledge which we have on site, which is happily shared. And of course, once we've produced the product and manufactured, fabricated it for you, there's the system test. That could be optical performance testing, but it could also be environmental testing. So whether that would be shock and vibration, high temperature storage, some damp heat testing, or even we often use external test houses where there's some more esoteric requirements for the system tests. As Pete mentioned, for space, there could be some vacuum testing, or even some very high shock and vibration testing of several thousand G. So that's something we look to incorporate all the time. And if we can't do this internally, we would do this externally. So if I just run through and sort of bring this all together, Gooch & Housego would love to be a one-stop shop where we can supply these components into your systems, whether that's the passive components or the DFBs, the fibre hues for switching and frequency shifting, amplifiers, and the PDR for detection, but also to be a manufacturing partner. If we can help with that, with the volume manufacture and feedback into your design at an earlier point, then that's absolutely something we'd love to do. So thank you very much for joining us today. I'd like to hand you back over to Adrian Chance, and we can answer some questions if you have any. Thank you very much.
Thank you, Sam, and welcome back to the panel as well, Toby and Pete, to answer a few questions. We've had a few interesting questions in during the course of the webinar, so I'd like to put these to the panel now. So first of all, gentlemen, first question: is it possible to have a picosecond pulse?
I'll take that one if you like. A picosecond pulse. We would probably need a different modulator technology. I think probably the Acoustic modulator is probably not going to get down to that kind of level. There are other modulator techniques that we use, such as electro-optic modulators. They can be somewhat faster, but they don't have the they don't always have the same power handling capability, which might not be a problem, obviously, if the pulse is generated before the amplifier. The other thing that can be done is sort of direct modulation on a laser. You can get down to that sort of level by direct modulation. The only snag there is that the change in the current by modulating actually causes a broadening of the line width, as I mentioned, and therefore you can't have a narrow line width at the same time. But there are sort of other techniques, and yeah, we'd certainly be interested to have a crack at that problem if there was a system application.
Thank you, Pete. Next question. I sharing this around, perhaps Toby or Sam. Is G&H rather involved with the laser light source?
Yes, it is. We make the DFB lasers, so at different wavelengths, very narrow line width DFB lasers. We don't make an ultra narrow line width source, but our DFB laser does get around to the 100 kilohertz level or so, which is perfectly adequate for many applications.
Thank you. The next question, I don't mind who answers this really. It seems that this only applies to fibre-based systems. How would we apply this to a free space system that sends and receives light, like a flash LiDAR system?
Well, I mean, a lot of the applications actually that we do have for this are actually free space. We do have very much a mixture. Obviously, we're using the fiber-based components to actually generate the source, generate the pulses and the initial laser light, because the components are widely available, cost-effective, and very reliable. And it's a great way. Using fiber optic amplifiers is a great way to generate high power short pulses. And then essentially, in order to to be applicable to free space, I think Toby did mention early on, you essentially have a fiber optic collimator, and that can be anything from a small 5mm diameter or less lens to produce a very small beam, or if you're looking to range over much longer distances and sense over much longer distances, then you would have a much larger collimator to produce a wider, larger diameter beam, which you can essentially keep collimated over a longer distance. And we do have several customers that are kind of active in that area. So I think most of the stuff we talked about is applicable in both areas. Obviously, the collection of light again needs a collimator to collect light into the fiber itself. And there are other ways of doing it. You can actually have a collimator and collimate the light directly onto a photo detector, for instance, if you didn't want to, or you couldn't couple back into fiber. So,
thank you, Pete. That's okay. Great. Thank you very much. Next question. Forgive me if I'm not reading this correctly. Is it a PIN receiver or a PIN-TIA inside your coherent receiver?
Well, we have 4 photodiodes inside there, and they're all pins, PIN structures.
Pin. Great.
Yeah, pin.
Okay, thank you. Do we have, so the question says, do you have sensitivity to atmospheric transmission LiDAR? So not wind and not hard returns.
Do we have what, sorry?
Right, sensitivity to atmospheric transmission LiDAR. I think it means do the modules does the technology account or allow for atmospheric transmission of LiDAR signals?
Well, it certainly does, and I mean, it sounds, maybe that's more of a question for the sort of systems engineers. There are ways, we're aware of sort of various techniques to be able to compensate for these things. As G&H, we're involved very much in the subsystems and the core source and receiver, but a lot of the techniques that's involved in the software processing, in order to extract the signals, we're not really active in. That's definitely more in an area for our customers, really.
Okay.
Yeah. Well, sorry if I'm getting the wrong end of the stick for the question, but
that's correct. Can the LiDAR system be used to form an image, and what is the depth resolution with the receiver?
Right. Well, it certainly could be. Again, that's very much a higher level systems aspect to it. But of course, the Lidar system is in a way it's similar to you know, to the kind of the systems that are being considered for automotive Lidar, which do form three-dimensional images. Now, our systems are generally, we're not targeting that kind of market because of sort of various aspects. One aspect of it is that actually the signals that our systems need to detect in our customer systems is the signals are very, very low level. We're looking, you know, I mean, for instance, the PDR receiver sensitivity is in the region of something like about 110 dBs. So we're looking at, you know, we can pick up scattered signals from the atmosphere, which as a function of distance, a range. So, and it's obviously that signal is a distributed return. So people can measure, for instance, measure the wind speed over that range, or detect gases or whatever in you know, over that range. So the signal levels are very much lower than would be used in a typical Lidar, automotive Lidar system, because in those systems you're looking for real returns from a physical object, which would naturally give you obviously still small, but it's somewhat larger than we would be detecting. But nevertheless, I mean, you know, it's in a way, it's in general, the broad brush principles are the same, and therefore, you know, if you designed a system around that, then certainly these systems could produce those kind of 3D image maps.
Thank you, thank you. Are you able to say or able to sort of say the optical materials used in the modulator?
Yeah, yes, we can say that, I think. It depends on the wavelength we're operating at. We have a range of materials that we can use at Gooch & Housego, G&H. Primarily, we use tellurium dioxide. For some high-speed applications, we use silicon. Those are our main acousto-optic materials. For very low RF power applications, where perhaps power consumption is a consideration, maybe the system's running off a battery or in some remote location, then we have a material called Amptia, and that requires very low RF powers to generate the acoustic grating that Peter spoke about, and that operates at just maybe a fraction of a watt compared to other acousto-optic devices that operate at several watts. So yeah, so we have a range of materials. Most commonly, we use tellurium dioxide that we grow in the Gooch & Housego factory in Cleveland in the USA. So we're completely vertically integrated with TeO2, but we are able to use other materials and do often use other materials.
Thank you, Toby. A couple more questions before we close off, if we can. So I think the answer to the question is yes, but you might want to expand upon this. Do we know the way to combine wavelengths from 1300 to 2400 nanometers and collimate them?
Well, it's not something we do commonly, but I think we could work out a way to do that if we had to, yes.
Great, thank you. I just one or two more questions, if that's okay. The Fibre VQ can frequency shift. Can it shift the frequency up or down, or both, I suppose?
Yes, yeah. I mean, that's right. I mean, I'm not sure what I mentioned in the presentation there, but certainly depending on the alignment of the device, we can get an upshift or a downshift in frequency, which, you know, and sometimes it's not that critical to the customer, but obviously, you know, other times it is, and we can control that, yeah, quite easily. Yeah.
Right. Well, I think we've taken up the full hour. I very much appreciate the questions, so the people who have answered and the people who are turning up and listening to us. We will have a record of all the questions asked. So if we haven't answered your question, we will do so by email over the coming days. Someone asked if we will make available the slides from the presentation, and we will aim to do that by the early part of next week. So yes, really makes me thank you once more. and we look forward to being in touch with you.
Yeah, thanks very much. Bye-bye.